Share we'll be up to. So I think for this talk, it will be mostly around applying kind of conformal prediction and extend it to graph problem. But I think, for me personally, I work on like biological networks, and so it has lots of application in that area. But unfortunately, in the slides, I didn't mention a lot about the application to biology. But I think we can, of course, discuss it later when we finish that.
Yeah.
Sounds good. Let's get started. So cool. Yeah, first I want to emphasize this is a joint work with amazing collaborators in Emmanuel and Yuri. So today I'll talk about, how do we get like a reliable uncertainty estimate for graph structure data, and what are some of the unique challenges when we extend the framework of conformal prediction to graph data, and also we develop a way to kind of reduce the to make it efficient and to make it really kind of usable for the graph setting. So just to motivate a bit, as you probably know, that graph is everywhere. Like there's like social networks, transportation network, internet network, financial network, patient network, and biological network. And so it's like everywhere. Everywhere there's like a relational kind of interaction type of things, then it can be naturally represented as a graph. So for example, in the case of biological network, right, any entities in our body can be represented as a node. But the node itself does not really function too much, because it's the how this, for example, like a protein cell does not function, but it's the contextual information, like how the protein interacts with another protein, and how these protein complex function with other protein complex. These kind of naturally occurring relational information that makes things happening. So given this kind of biological or like any kind of network, we are interested in lots of predictive tasks. So here, in the case of social network, natural question is like, okay, will this person A and B become friends? And for node level prediction, it would be like, will this person X stop using Facebook or some other social network platform? And in the case of biological network, the link level prediction will be like, will drug X bind protein B? And then for node level prediction, it will be like, what is the function of this protein, right? So there will be so many interesting predictive tasks can be formulated over graph. And these answers are also really kind of valuable for business and for science discoveries. So recently there's a class of model called graph neural networks that is really powerful because it directly operates over the graph, and it can learn end-to-end based on some loss function defined over a specific task, and it just automatically pick up what is useful in the graph structures and also the node features itself, and then you can do predictions. It can be classification, regression, or anything. So today we'll talk about how do we use graph networks later, but I think here just motivate a bit on this. So we're basically focusing on GNNs. So as these GNNs are becoming more popular and more and more practitioners are going to use them, they just notice an important problem, right? Because in many of these safety critical or high stake settings, these errors have huge costs. For example, if we apply GNN on like a patient network and we want to diagnose a patient, which node is a patient, then this error corresponds to wrong diagnosis. And if we apply GNN on like drug discovery network, these errors could correspond to wasted experiments. And GNN on financial network, then it's like undetected fraud. So in all of this setting, these errors have huge cost. And as the errors accumulate, just people stop trusting these models, and we really don't want that to happen. So what should we do in this setting? We want to produce some kind of estimated model uncertainty. And I think there are many ways to quantify uncertainty, but in this talk, we'll focus on one type of uncertainty quantification, which is instead of giving a point prediction, we'll give a range of plausible predictions. So here, just example for classification, we're looking at prediction set instead of prediction, like a single prediction. And in the case of regression, we're looking at a prediction interval instead of a single scalar output. And the key benefits of this having this prediction set is, first of all, it's very meaningful. Instead of just giving like one diagnosis, you have a meaningful range of values of diagnosis, which is can inform decision making. In addition, the size of this interval of these prediction set is also signals the level of uncertainties. So if a set is super large, then probably the model is not that certain. And it also enables a notion of reliability, which I will talk about right now. And basically we want to measure, how good are these prediction sets or intervals. So there are two main metrics. The first one is coverage. We're basically counting the percentage of testing points where the ground truth falls into the prediction set or in interval. And here is an example, right? This is ground truth and this is a prediction set, and if it falls into the prediction set, then it's good, and vice versa. And similarly, in case of regression. And we know that if given the coverage metric is actually pretty interesting, because if we think about it as like a truly trustworthy machine learning model, we have 100% of coverage. But as we know, this prediction is also constructed, right? It's not like from an oracle. So it has to have some errors. So 100% is not possible. So now we're thinking about maybe we can make it step back, take a step back, and just instead of 100%, we just control it with some predefined guarantees. And this guarantee is very nice because now you can make claims like, okay, I have 99% of predicted diagnosis that provably includes ground truth. And this way, it just directly leads to the model trust and solve the problem that I mentioned before when we deploy GNN systems to this to this safety critical or like high stake settings. So just to formulate a bit, we want to give a predefined target coverage level. We want to reach this coverage level with some guarantees. And we are saying that the reliability and trust equals to coverage guarantees. Okay, so coverage guarantee is definitely one important metric, but also another important metric is called inefficiency, because if you imagine like you can arbitrarily create a very large prediction set or very large prediction intervals, and it will have 100% coverage. But in reality, these are not that useful, since although it has coverage guarantee, but this such a wide range, you can make them for every prediction point, so for every testing set. It indeed achieves coverage guarantee, but it's not practically usable. So in this sense, we also need to quantify some inefficiency. So basically, it's the size of the prediction set of size of the length of the prediction intervals, right? So we always prefer the ones that are small. So small prediction set and shorter prediction intervals. So, and of course, while ensuring coverage guarantees. So for this goal, we want to, for graph structure data, we want to achieve coverage guarantees while minimizing inefficiency. So that is the goal of this talk, and also we will describe a method trying to do that. So the plan so that was kind of a motivation of why do we care about graph uncertainty quantification, and what are the metrics that we want to optimize over. So the plan for today, I'll first give an introduction to kind of machine learning over graphs, which I think some folks may not be familiar. So I'll give a more kind of a in-depth analysis on this. And for the conformal prediction, I believe folks are very familiar. So I'll give a very quick overview of the conformal prediction, and just to write kind of the notation that we're going to use, and just to make things on the same page. And then I will talk about how do we extend conformal prediction for graph structure data. What are the conditions that it requires for the graph models to achieve conformability, and when will this conformability not hold for graph data. So we will discuss this kind of a coverage guarantee aspect of this conformal prediction for graph data. And in the end, I'll also talk about a method to improve efficiency significantly when we use conformal prediction for graph structure data. So that's the plan for today, and we can get started. So first, how do we do machine learning over graphs? So what is a graph? Graph is basically consists of three things: a set of nodes, a set of edges, and also node features. So here, just like a minimalistic graph. So we have like 4 nodes. So this is the vertex set 1, 2, 3, 4. and the edge set is 1, 2, 1, 4, 2, 4, and 3, 4. It's basically we will have a edge if there's an edge between these two nodes. And also another important thing is the node feature. So for each node, it has some meta information that is very useful for predictive tasks. For example, in the case of protein, then maybe there's some like features about the protein, like some function annotations or like some structural information. And these also are information that we want to incorporate into the model. And so for the edge representation, another common way is to represent it as an adjacency matrix, where each item here is basically corresponds to row I and the node I and node J, and it becomes a 1 if there's an edge, and it's a 0 if there's no edge. So this is a basic representation of the graph. And some common tasks in graph machine learning, there would be kind of node level prediction, which I think is most popular. And there's also like edge level prediction, for example, predicting protein interactions, or like graph level prediction. If like the entire graph is some for example, small molecule, like molecule structure, then maybe some graph level task is to predict the property of this molecule. But in this talk, we'll focus on the node level predictions. And the goal is to, given this network, we have some unseen nodes in the graph. We don't have label for them. For example, some proteins we don't have, or some drugs we don't have kind of experiment done on them, and we're interested in predicting these properties for these unlabeled nodes. So that is the goal, and we're looking at both classification and also regression. So the goal of graph representation learning is basically similar to, for example, CNN for vision. We just want to directly operate over the graph structures, and then gather as much information as possible, and then produce nice node embeddings. So here we basically learn a function f parameterized by theta, where we map each node to a latent embeddings. And this latent embedding can be then used to for all kinds of prediction tasks. Right, and we also want to do it in an end-to-end fashion. So we want to directly produce a node embedding, which is fine-tuned based on the prediction tasks. And so now the question is, how do we map this node U to node embedding? So the principle of getting this embedding is basically we want the embedding to capture the structures in the networks, right? And also the node attributes, like node features for each node. So here we're basically saying maybe we want to have some neural network design such that it can transform based on the local network information and also the node attribute itself. And hopefully after transformation of every node in the graph, when we embed them into the same embedding space, this embedding space captures all the information from the network. So GNN is actually a kind of a way to do it. So basically the key idea is like, for each target node, we look at its local neighborhood, and we do aggregation of information from its local neighborhood. So for example, here's the target node A. We can look at its local neighborhood, which is B, C, and D. And for each node in a second layer, we can also look at its neighborhood. Like for example, B, we're looking at A and C, and C, we're looking at A, B, E, and F. So we can do this recursively for many layers for many layers in the graph. So basically, there are like 3 steps for GNNs, so the first step is the neural message passing, which is basically for each node from the neighborhood, we can compute some necessary information that are needed to be aggregated to the target node, right? So here we just calculate a message for every neighborhood around this A. So we have a message for B, have a message for C, and a message for D. And second step is to aggregate these messages together to a single message. And then using this single message, we update the target node embeddings. So that's the kind of for each layer, we just do these 3 simple steps. So just to give a more concrete example, we're using a graph convolutional networks. What it does is basically for the first step, neural message passing, it takes in the last layer embedding of the node. Oh, also I forgot to mention. So at the layer 0, each node will be initialized as its own node features. So at layer 1, for example, it will just look at layer 0 information, but at layer 2, it will look at layer 1 information. So this is how we can update the embeddings. Oh, sorry. And so here, so for example, the graph convolution network, what it basically does is for neural message passing, the message is just the last layer embeddings for the node, for the node from the neighbors. So just simply takes last layer embedding of the neighbors and then do that for every node. And then the second step for the aggregation, it basically takes the average across these node embeddings. But of course, we can design lots of different aggregation operators. It can be like sum, it can be even like more complicated one like LSTM, and also like some MLP or things like that. So basically we just aggregate information from the local neighborhoods. And now you have a single vector that represents all the neighboring information. And the last but not least, we just update the embedding for this target node. And the way we do update is basically we first have a learnable weights for the message, and also have a learnable weight for the target node itself, and also have a nonlinear transformation. So this corresponds to one layer of the graph neural network update. And then we can just build upon each many layers. And then in the end, we just get a node representation that is rich with network structure information. And based on this node embedding, we can then do prediction. So this is just put it together for GCN, right? So here basically what it does is look at each local neighborhood, what's the last layer embedding, take an average, and then do the nonlinear transformation. And here I want to emphasize here, like here across node, we have the same copy of the weight right here. Okay, so we don't create a weight for every node. We just have the shared parameters of W and B, which is the size of the hidden dimensions. So it's not dependent on the network structures, but it's dependent on the dimension size of the features. So here, this enables us to compute the node embedding for every node in the graph pretty efficiently. So that's an example of the graph neural networks, but there's lots of variants, but all following similar styles of these message passing schemes. Okay, nice. So I will also talk about some setups of the graph neural network that is typical and also very are going to be used when we extend conformal prediction to graphs. So here, the first of all is the data splits. So in default, most of the GNNs, at least in the benchmarks, they're currently just running like random data splits. I think this is also a pretty realistic assumption because, for example, you're looking at the social network, then the unlabeled person is kind of spread out across the networks. So you can just simply do like random data split. But of course, there are also more complicated splits. But here we're going to assume we're using random data split.
But also, is the data point here like an entire network, or do you have like many networks? Because this will depend on the application, right? Like in social networks, you just have one Twitter.
Exactly.
So how do you do training and testing in that case?
So here we
one by the graph structure.
Yeah, so here we just have a one big graph. So we don't have like multiple graphs. So we just have one very large graph, and then we do split within this graph, right? So you have, for example, 1 million nodes. You randomly pick, I don't know, like 10,000 nodes for the calibration and 10,000 nodes for testing sets.
And do you keep the edges between the nodes that you picked only?
Oh yeah, so I will talk about that right now. So there's a distinction between transductive and inductive problems. So in transductive problem, the graph is fixed. So all of these unlabeled nodes, so we keep all the edges in the graph, right? So because the graph is kind of fixed. So it's just we don't have labels for these nodes, right? For example, if you have a biological network, all the nodes are already there. We only have 20,000-ish proteins, so it's already fixed in the network. we just don't have the labels for these proteins. Okay, so in transductive setting, what it does is the graph is fixed, and all of these nodes are observable in the training graph, and the calibration testing nodes features are used in the message passing, and for example, like predict the protein functions. But on the contrast, there's another problem setting called inductive node level predictions, and in this setting, new like evaluation node is coming on the fly. And in this setting, graph is definitely not fixed. So for example, in social network, you have new user comes in, right? And then in this way, a new user is kind of linked to existing ones. And the new users links are not seen in the training graph. So, and also the message passing does not know this information from the new calibration test nodes. All right. So this is a very significant distinction, and we also talk about in which prediction settings the conformal prediction will work and which problem does not work. Yeah. Cool. So that's all the necessary information we need for when we talk about conformer for graphic data. And next, I'll quickly go through conformer predictions. I think people are very familiar with this. So here, just to motivate us a bit, right? We first benchmarked some of the state-of-the-art uncertainty quantification method for graph structure for GNNs, and we benchmarked it across many different data set. And as you kind of expected, the coverage guarantee is fair to achieve, right? So here, there are many different meta models. The upper table is for classification, and the bottom table is the for regression. I think basically they all produce heuristic uncertainty, and there's no kind of guarantees designed for these models. And conformal prediction is a method just to turn this heuristic uncertainty into a guaranteed uncertainties. And it has various nice properties, like it has theoretic guarantees on finite sample, and it has distribution-free, model agnostic, and also a post-hoc wrapper. So there's no training modification, which is very nice for large machine learning models. So here I just describe the steps to get this prediction set of an interval. So here we first do the training and calibration and testing data, and we have some predefined coverage level. And given the training set, we have a feed into machine learning model. And after training, we want for any testing point, we can get some prediction scores. And the first step is we want to define some heuristic uncertainties. And we can, so here I have run an example on classification, which is basically the softmax score. And basically the softmax score is a measure of heuristic uncertainty, right? Because it's high, then basically the model has more confidence towards that label. And step two is want to define some non-conformity score, where the non-conformity score function defines how much label Y conforms to the prediction at X. For one example, for the softmax score, it would just be taking 1 minus the softmax score, right? Because the softmax score itself has the reverse direction, because non-conformity score we want it higher when the model has lower confidence. So we just simply do like 1 minus this thing. And then for quantile computation, the next step is basically we take the calibration data, we calculate the non-conformity score for each label, for the ground truth label for each calibration data. And we can then collect all of these non-conformity scores, and then we can also aggregate them. And here's the distribution of the non-conformity score from the calibration data points. And here's basically for each calibration data, we can calculate like the length of these yellow arrows are the non-conformity scores. And next step, we can just take the quantile of these non-conformity scores. And for example, 95% quantile here, this eta hat is the quantile for the ground truth, well, for the calibration data point and the ground truth non-conformity scores. So basically the meaning of this is like 95% of the calibration truth labels have non-conformity score below this eta hat. And we have this nice prediction set where it's basically the set of labels where non-conformity scores are smaller than eta hat. And for example, here we have this new testing point, and we can compute the non-conformity score for every labels. And then we just look at every labels if it is smaller than the eta hat, and if it's smaller, then we just use that as the prediction set. And yeah, so I think like this procedure is pretty general for the conformal predictions. And here I also want to do it for regression. The step one is to define some heuristic uncertainty. Here it can be using a quantile regression model. We'll get an upper quantile and a lower quantile. And for nonconformity score, we can define the nonconformity score as the distance from the ground truth to the closest quantile. This also measures the nonconformity and with the right direction. With the right direction. And for the quantitative computation, it's pretty similar, so I didn't show here. And for the integral construction, it's basically the range of labels that where the prediction where the non-conformity score is smaller than the eta hat. So here, just basically adjust the prediction quantile slightly such that it has a guarantee, which is this one. Because so the reason why we do all of these steps is because we want to achieve some coverage guarantees, which is basically from this nice paper, given the exchangeability between calibration set and testing data points, and the probability of the ground truth forcing the prediction set is larger than 1 minus alpha. And this basically enables us to make claims like 99% of the diagonals set contains the true label provably. So the only assumption here for these to hold is exchangeability, which is basically given calibration data and at any test point, we can permute these calibration data and test point, and it holds that the probability of these of this sequence is same for any permutations. So here is an example. For example, we have a bag of colored balls, and basically the probability of having this color sequence is same to any permutation of this color sequence. Cool. So hopefully that's a very quick, but I think you guys are all familiar with this, so I made it really quick. But basically that's what we're going to use all the notations for conformal predictions. And the conformal predictions has been really applied to many different problems in vision, natural language processing, and so on. I think the main reason why they are applicable is like, we assume that the calibration and test point in these problems are independent and identically distributed. And IID automatically implies exchangeability. And so and for them we can make a really nice prediction set like what we have here, right? But now the question is, does exchangeability hold for graph structure data? So basically, if we think about it in this transductive setting where we have the training node, we have the calibration node, and we have the testing nodes, and there are dependencies between testing and calibration nodes, right? Because if imagine when you compute the node embedding for the testing or calibration node, it is taking the local neighborhood around this node, right? So if the local neighborhood directly includes other testing or calibration node, then it's definitely not in IID anymore. So this means that this simple assumption of IID we cannot utilize for graph structure data. Okay. And as I mentioned, like because this massive passing during the training includes the calibration and the test set. So just to make it more clear, so previously when we calculate the nonconformity scores, we have this XY, and it's depending on ZV, where the Z is basically X and Y here. So I forgot the notations. And this ZV all coming from the training and the validation data. But now when we calculate the nonconformity score for graph structure data, it is dependent on much more information, right? First of all, the calibration at testing data point are already seen in the training. And here we just is the X. We of course we don't observe the label here, but we do see the node features in the training. And also there are lots of graph dependencies that can make things really complicated. Okay,
so why do you need to include the calibration nodes in the message passing?
can you repeat the question?
I mean, are you including the calibration nodes in the training?
Yeah. So we have so in the transductive setting, so all of these nodes are already in the graph, right? So we don't want to explicitly remove these calibration data points in some sense. So it's already in the graph. And for example, the calibration node, the node features are already used when we compute the embedding for these training nodes, right? But it's just we don't have the labels. We just have the node embeddings is calculated, right?
Oh, so when you do the training, you hide the labels only, but you keep the nodes and the connections.
Exactly. So the graph is like fixed graph. So it's just like a fixed graph, and it has to be used, right? Otherwise, it's weird that we arbitrarily remove some of the nodes just for the sake of constructing conformal prediction. Yeah.
I had another question. So, what information about the calibration and tests like that we're using during training? Is it just like we're using the nodes because they have connections to the nodes that are there in training? We do not use any information about what their like the learnable node information is. Like I didn't exactly understand what we're using in the while training for the calibration and test nodes.
Yeah. So that's a good question. So basically, I think I'll go back to the graph neural network message passing. I think this will make it very clear. So for example, this A is a training node, right? During the training, we optimize this node embeddings, right? But this B, for example, is unlabeled and it's a calibration node. And so during training, it is already using the embeddings or like node features from this node B when we calculate the training nodes. Okay. So there's like dependencies, right? So the calibration node is used here. Although we're not like trained directly over this calibration node, we're not like predicting this label or anything, but it's implicitly used to train the other training nodes since it's all connected, right? So that's what.
Sorry.
Yeah, go ahead. Sorry.
Yeah, so we're not updating these embeddings at any point. We're just using the initialized embeddings, which may not be optimal. But we're using them to update it.
So actually the calibration node after the model learning, after the training all of these training nodes, because so the way we calculate this calibration node is also using this local neighborhood aggregations, right? So it's still using the W and B, which is updated during training. So for the calibration node, we're also still using when we compute the calibration node embeddings, we're still using the W and B which is trained using the training nodes. Okay, so it's not just using the node feature like the raw node features. We are using the updated node features.
So we're updating B as well at every point when we're updating A.
Sorry, can you repeat? I think can you move closer to the speaker? I cannot hear you very clearly. Yeah.
And I was thinking we're updating B as well as during every training step.
Yeah, exactly. So the W and B, they are updated. So basically, I think just give a more concrete example, right? So for example, you want to predict the protein's function. You have some labels. You have label for this label A, node A, and then after you get this representation using this aggregation steps, you get an updated node embedding A, right? And then you do a binary cross entropy loss, for example, for these protein functions. And then the loss will back propagate to this W and B, right? Although we're not, so although the loss never operate over the node embedding B, but because it updates W and B, and the way we calculate the calibration node embedding is also using the W and B. So it's also kind of affected already by the training process. Yeah, so that's what we mean, like calibration and testing node, they're actually affected in the training. We're in the conventional conformal prediction setting, right? This new image in the testing and calibration data, they're never seen in the training. They're just completely new. They just take the input and then they just get a prediction score. But here in the graph neural networks, we have the calibration and testing points during the training massively passing. So that's also what makes things really tricky, which I will talk about, conformal validity and things like that.
Okay. Thank you.
Yeah, that's a great question to clarify. Cool. So let's see. Cool. Yeah. So now we have these thing, and then we're just thinking about what are some of the problem scenarios, or like maybe some conditions of the graph structure data, or like graph learning that can make conformal prediction hold. And then we find that in the specific setting of transductive no-level predictions on a random data split, the graph exchangeability holds, given a condition called permutation invariance of the model. So I'll unpack this a lot, but here I also want to first say that the transductive no-level prediction problem on a random data split is a very kind of popular, which is kind of actually the default GNN evaluation scheme. So it's actually a very wide range of problem settings. So this theory actually shows that the conformal prediction can be applied to this problem. Okay, and so here, what do we mean by permutation invariance? So permutation invariance is basically for any permutation of the calibration and the testing nodes, the non-conformity score V obeys these equations, which basically is saying that no matter how you permute the calibration and test set, the non-conformity score always stay the same. So we'll talk about how GNN can satisfy these permutation invariance conditions, but for now, let's just assume that this assumption holds, and I will go through given this assumption holds, why this graph exchangeable holds, and then we can go backwards to see why GNN has this permutation invariance condition. Okay, so that's the plan for the next few slides. So first, what do we mean by permutation? So given this permutation invariant, why does graph exchangeability hold? So because given this permutation invariance, we can say whatever subset is designated as calibration set, the non-conformity score stay the same. So it's almost like now the non-conformity score becomes a set instead of a sequence, right? So for example, here is a calibration and testing node, and this is an order 1. And we can also permute them into a different order, which is like EA, B, C path. And no matter how you permute it, the permutation invariance condition defines that to have the exact same non-conformity scores. Okay, so this is what assumption that gives us. So no matter how you permute the calibration testing node, the prediction score are the same, and the permutation and the non-conformity scores are the same.
So it's the same in distribution, right?
It's actually the same score. Okay.
Oh, the exact same score.
Yeah, the exact same score.
Okay.
Yeah. So I understand it's a kind of a stringent condition, because here we're not assuming IID anymore. So we need to make it extremely stringent to make it work. Okay. So now here we're basically saying for any permutation orders, the non-conformity scores are the exact same. And now because of the random data split, the probability of having each of these permutations is actually the same, right? Because it's the random data split. We can even explicitly calculate the probability score, which is 1 divided by the number of n plus m, which is the number of calibration and the number of testing set, and choose n, which is the number of calibration data, right? So this basically defines we have the same probability of each permutation of the calibration and testing data. And this just directly gives us exchangeability. Okay, so that's why we can say the graph exchangeability holds given permutation invariance.
I had a question.
Yeah.
I think you mentioned, but I may have missed. So we're assuming the calibration and testing is from the same underlying distribution.
Okay, sorry, can you elaborate?
The calibration and testing is like from the same underlying distribution, which may be different from training, or is it like not different from training? As in the calibration and the test points that we have here is the underlying distribution that these points are from. Is it like the same, and is it like same as training, or like it's a different?
No, we actually don't make assumption of this distribution to be the same as training, right?
Okay.
Yeah, because here we're just saying no matter, so first of all, the permutation invariance give the exact prediction scores, and then no matter how you permute them, it's the exact same prediction score. And the randomness here is coming from the random data splits. It does not come from dependencies of the training and validation, and calibration testing have the same distribution, right? So that's the difference from in a conventional conformal prediction settings where we make it work because we're assuming the independence or independent and identical distribution. But now we're saying each permutation, because it permutation invariance, it has same prediction score and same non-conformity scores, and then the probability of each permutation order is the same. And then we can directly implies exchangeability. So we're not relying on IID to make it exchangeable. We're actually relying on this random data split and permutation invariance to make it exchangeable.
So the random data split assumption, like in a practical problem where you have a graph, you probably the testing environment is not something that you have control over, right? Like you want to make predictions or inferences about some nodes, and these nodes are truly have unknown labels, and they might be correlated to each other. Like the assumption of randomly splitting calibration and testing might not hold because the things that you are interested in making inferences about are really unknown, right? It's not that you have labeled data and you're hiding the labels and you're randomly splitting.
Exactly.
And I think we make sure that this assumption holds in like a protein network, for instance.
Exactly. Yeah, I think that's a really good point because so I think here we just demonstrated with using a random data split to make the probability of the sequence equal. But in reality, we can observe two things. The first thing is indeed there are many problems, for example, in social networks, where the new evaluation set is relatively random, spread across the entire networks. So there's definitely problem where the random data split holds in some sense. I mean, of course, not like maybe not like in the perfect sense, but like the random data split is a good approximation of the real world use case. But there's also like a class of problem, the real problem does not have random data splits, which we will talk about later. This does not hold anymore. Okay, so here I'm just talking about the perfect world where we have these conditions. If this holds true, then we'll have the conformal validity for graph structure data. But there's also many scenarios for future works and that make conformal prediction does not hold for graph data, which I will talk about later.
And just second, another question, like, does this assumption like limit the structure of the graph that you need like for any subset of the graph to have the same conformity score? Does this imply anything about the structures of the graph where that would hold, or is it?
Yeah, so I'll talk about the permutation invariance condition. And so this is the condition that we impose over the graph data or all the graph neural networks that we require to make it in order to make it work. Yeah. So here we're just assuming permutation invariance, but now we're saying, okay, is GNN or like graph structure data really permutation invariant? So for example, here you have you have the same graph structure, but you have different orders, right? So the A, B, C, D, E, F is here is in this order plan, and for this order plan 2, this is F, E, D, C, B, A. So ideally, you won't have the prediction to be the same, right? Because there's the same graph structure, it's just different permutations of the order of the nodes, right? And then if we look at how do we calculate the node embeddings, actually the GNNs is mostly permutation invariant depending on the neighborhood aggregation factors. Right? For example, the first one, the neural message passing here, each message mapped from a node to another, this is not sensitive to the permutation orders, right? Here we'll just look at the features of the node. No matter what is the index of the node, the features of the node stays the same. And also here the B is the target node. No matter what is the index of this node, we're still just using the node embedding to calculate the message. So the message, the neural message passing is not permutation sensitive. And for neighborhood aggregation, it is permutation sensitive, because if we input A and C, if we shift the order, if the permutation operator is not invariant, then it will change the node embedding of the target node. It will change the embedding of the at this M and then change the embedding of target nodes, right? So for example, if the aggregation function is like a sum, average, or like some permutation invariant operator, then everything will be permutation invariant. But if the aggregation operator is some complicated non like neural network like LSTM, which is actually popular. One popular model is actually using these aggregators. But in that case, it's not permutation invariant anymore, right? Because if you switch the order that you feed into the model, the node embedding will change, and in turn, which will change the non-conformity scores. Yeah. So here, this is what we want to pose over the graph neural networks, and also basically we want to pose the constraint of permutation invariant for this aggregation operators. And here, for example, GCN, this is a permutation invariant. Right? So here, just a summary of proof, we first like given a permutation invariant aggregation operator in GN, then we can see the predictions are permutation invariant. And then because the non-conformity score is basically derived from the prediction scores, then the non-conformity scores are permutation invariant. And then because we're doing like random split, so now we just basically get the randomness from the split instead of the graph. Now we have exchangeability for graphs. Okay, so that is the idea for this theorem. And now we talk about, when we're not hold. I think many of you already pointed out, like, first of all, is like, if the model is not permutation invariant, then it will change the non-conformity scores, and then it will not hold. So for example, actually there's a class of traditional model that directly operates over the adjacency matrix. Okay, and then in this case, if you permute the order of the nodes, then the adjacency matrix will change. And then and the MLP is actually not permutation invariant. So it will change the non-conformity score, which makes the theorem break down. And also another scenario is like when the permutation invariant operator is like LSTM or like some other non-permutation invariant aggregation operator, then this non-conformity score will also change, and then the theorem also breaks down. And also, just to make it more relevant, right? Because in the inductive node-level problem, we also don't have the theorem hold. Because in inductive node-level prediction, here's two permutation plans, right? In the permutation plan 1, because it's coming on the fly, we first have this calibration data points attached to the graph, and then we have a new testing point coming in, right? And this is another permutation plan where we have these 3 nodes attached to the graph, and then we have a new node comes in. And if we calculate the non-conformity score for every of these nodes, the score will actually change, because this, when we calculate the node embedding, it depends on the local neighborhood, right? Because for example, when we calculate this embedding here, it has information of these nodes. But when we calculate the node embedding here, because this one comes later, we don't have this node in the graph to calculate the node embeddings. So the non-conformity score and also the prediction score will be different for this permutation plan 1 and permutation plan 2. So this way, the non-conformity score also does not hold anymore. So in the inductive setting, we don't have these guarantees on the coverage. And last but not least, I think you may also mention, like, when data split is not random, then it's dependent on the split. Maybe it requires a stronger kind of maybe for future work, we can define some constraint on the split that makes the exchangeability hold. But if it's like a non-random split, typically we don't have this probability equal anymore, since here we in the proof we're using this randomness to get the probability of each permutations. So under different other split types, exchangeability may not hold. So cool. So that was the kind of a summary on conformability for graph data. So I think it's more like a discussion on why and how and when conformal prediction hold for graph data. And but in reality, for the transductive setting and for random data split, which is pretty prevalent in the GNN literature, we're happy to see that the conformability would hold for them. And next, given this coverage guarantee, I want to see maybe we can improve the efficiency for these methods. So I think how do we improve efficiency? Basically, I think our key observation here is like the GNN prediction scores are not optimized for conformal efficiency, right? If we look at the standard GNN training, it is optimized for MSE or like for like binary cross entropy, all these prediction laws. They are not aware of the downstream conformer step. And actually, there's recent studies on GNN prediction scores, and they analyze it, and they find that there's like overall underconfident trend. And so this means that the GNN prediction scores are really not kind of calibrated. And this also has some implication for conformal prediction, right? So this is just one implication, but there should be more complicated other implications. Here, for example, if the model is underconfident, given the same prediction scores, if you have a underconfident prediction score, then it's like more spread out. But if you have a calibrated, then maybe you have a more kind of standard, more kind of higher confidence for the right class. And then given the same quantile level, then for these prediction set, you will have a larger prediction set size and also lower efficiency. But for this one, if you correct it, then it has a higher efficiency. So this is the motivation, but there's maybe more complicated ways to for the prediction score to be changed such that we can optimize for the efficiency. But basically, this shows that maybe we can update the scores automatically to maximize efficiency. So here we're basically proposing a post hoc step that does not affect training, and then we can just adjust the prediction score slightly, such that it can optimize for efficiency directly. And how do we do that? Basically, there's one data analysis that we did. We find that there's rich topological information for the efficiency. So what we do in this analysis is we find pairs of nodes that are linked in the graph and also pair of nodes that are not linked in the graph. And we calculate the inefficiency for each of the node. And we calculate the difference between inefficiency for the linked node and for the non-linked node. And we find that the linked node have much smaller inefficiency gap compared to the unlinked node. So this basically suggests that the inefficiency actually has a topological root. And this also motivates us. Maybe we can use some network structures to improve the efficiency. So for example, we can update the prediction score of a node by looking at its neighboring nodes, right? Because if a node prediction score is not good, then we can maybe leverage information and correct this node's prediction score by looking at the neighboring nodes. So this data analysis motivates us to design a procedure to update the prediction score such that it can maximize efficiency. And we also want to pose some inductive bias or like symmetry to the prediction score update scheme, since we have this data analysis showing that this inefficiency has a topological nature. So here what we did is we, instead of just a simple maybe like applying MLP over the prediction scores to update the scores, we have a GNNs operate over the prediction scores. So for this new GNN, it will still use the same underlying graph structures, but it will have the node input is not the features of the node anymore. It's the prediction score from the base GNN. Okay, so if you think about a GNN, or if you like degenerate this GNN to a simple aggregation, it's basically taking average across the local neighborhood around the prediction score. So it's like a network smoothing of the prediction score, and this way, so this is just like one way to update the prediction score. But we have a more kind of nonlinear or like learnable way to update the prediction scores. So now the question is, how do we update this new GNN weight? So I think we want to, automatically approximate the inefficiency metrics such that the GNNs can learn to pick up useful information from the neighborhood to update the prediction scores. So we want to design a loss function to approximate the efficiency and directly learn to optimize over it. So here we just basically design a differentiable conformal proxy. And here I'll just go through each of these steps in making it differentiable. So for example, if we look at the heuristic uncertainties, then this is automatically differentiable, right? Because this is just the prediction score, and this is 1 minus the prediction score. And here the max operator is also differentiable because the gradient can just go to the maximum terms. And we look at the quantile, it's also differentiable. I mean, it's not differentiable itself, but there's like a smooth quantile operator that's pretty publicly available. Actually, the total quantile operator is already implemented this smooth operator, so you can get a gradient from this total quantile. And I think the last thing is the prediction set or interval size proxy. And for this one, for the prediction set size, it's not differentiable, because if you look at this one, it basically introduces like a step functions, right? So here we want, when a v is smaller than eta hat, we want to give it to a 1, and when the v is larger than eta hat is a 0, and then we basically sum up every possible labels for the single data points, and we also sum up every point to calculate the inefficiency metrics. And because of this, we basically do a simple smooth indicator function to make it differentiable. And here is basically a sigmoid with temperature set to a small value. And this way we have a kind of a smooth step functions. And now we can make it differentiable. And here is basically when the nonconformity score is smaller than eta hat, it will be a value close to 1. And when it's larger than eta hat, it will be a value close to 0. And then when we sum up every labels and also sum up every data points, then we just get a inefficiency proxy. And for the interval length, is actually we can derive it and make it differentiable, because it's just the eta hat plus this upper quantile and the eta hat. And the lower quantile minus the eta hat, and the difference and the length between them. So just to overview here, we have a method that update the prediction score as a correction step, and we basically simulate the conformer step, and we directly optimize the inefficiency of the downstream conformer predictions. And also to note that here we designed these calibration data set and testing data point by withholding some part of it in the calibration data. So we're not like touching the testing data. We just withhold some of the calibration data and use that for the correction. And we are only and for the holdout set, we also split into half. One is using calibration and one is using testing. So this way we can simulate the downstream conformer step. And also this entire step is also permutation invariant, so we can also still achieve coverage guarantees. So here now I want to show some results. So basically, I think I showed this slide before using the only on the UQ, only on the uncertainty quantification baseline models. But now, given this CFGNN, we find that we are able to achieve empirical marginal guarantees like marginal coverage guarantees over a large number of graph data points for both classification and also regression data. And we're also enable, and when we compare to the vanilla conformal prediction, we're also enable like much more inefficiency in the prediction set or prediction interval constructions. So here, the left table is for classification. You can see compared to the vanilla conformal prediction, we have a much smaller size of the prediction set. And for the regression, we also have a slight improvement on the inefficiency, which is in average 6%. So this basically shows the benefit of having this correction step. And another interesting thing, which we don't have a good explanation, is we also plot the empirical kind of conditional coverage. So conditional coverage is theoretically kind of not possible in practice to achieve the guarantees, but we can still do the empirical conditional coverage for the sake of comparisons. And we can see that compared to the vanilla conformal prediction, we're able to do pretty good on some of the features. So the way we compute these features is basically using a thing called worst slice coverage, where we take different slices based on these input features, and we compute the coverage in each of the slices, and we calculate and we use a worst coverage across these slices. Okay, so you can see that on a vanilla conformal prediction, the conditional coverage is not satisfied using these network heuristics features, but for our method, somehow it is able to be close to the target marginal coverage level. And also we did some like ablation study where we remove some key components. Like for example, we remove the inefficiency loss function. So this basically degenerates to some like network smoothing effects. And it also have some strong improvement, but it's far away from using inefficiency loss to automatically pick up which is useful. And also another ablation is basically we remove the topology awareness, but we use the inefficiency loss. So instead of a graph neural network, post kind of a constraint over the prediction score update, we just use a simple MLP to update the prediction scores. And in that case, also there's definitely some improvement, but it's not as good as when we have a topology aware correction model. And so there's also lots of sensitivity analysis, which here I demonstrate across different coverage level. We're able to see pretty robust prediction interval length reduction. And so that's kind of summarize all my work. And so there's some of the very interesting follow-ups in the last few months where we extend to the link prediction settings and link extension to like non-uniform split, extension to inductive setting, extension to edge exchangeability, and so on. So I think there's more and more work on making conformal prediction reliable in many more kind of application areas in the graph structure data. So in this paper, we kind of the first paper to describe in the transductive and low-level prediction problem, but looks like there's more recent work on kind of extending this framework to other GNN settings. So I think that sums up my talk, and thank you for listening. Yeah.
Oh, thank you so much.
Thank you.
One question regarding the training with awareness of the conformal prediction. Like, aren't all of these methods general? Like you can even do the same thing without GNNs?
Yeah, actually it is general. So you can apply it to, maybe the correction model, it would be nice to post some constraint. Like here we post constraint because we observe that there's some network information that can be leveraged. But if you update this correction model to be MLP, then it's like a super general approach. to update the prediction scores. Yeah. And also another good thing is here, you can also design the loss function, right? Here, basically, we differentialize the conformal proxy, and we kind of optimize over the inefficiency metrics. But maybe you can also optimize for other metrics, like you want to ensure that it's conditional valid. Then maybe you can look at some labels and then calculate the coverage for each label and then directly optimize over it. Or there's other desirable properties of conformal, like of the downstream model. You can also somehow manipulate the loss function and then to update the prediction scores.
In terms of, I know you didn't talk like specifically about like a specific application, but can you give us a sense of what the uncertainty sets would look like so that they are useful in like other this link prediction in social networks example or the protein example?
Yeah, definitely.
What would like Meta do with a prediction set if they have like a link prediction algorithm and it gives them a set instead of a score? Like how would people act on a set?
Yeah, I think that's super interesting. So I think on top of my head, I think the most direct application is when the prediction set has like the labels has and it has like a range of like for example in the patient diagnosis settings, right? So previously just give a one diagnosis, but we all know that the model make mistakes. Now if you have a range of diagnosis, and each diagnosis has lots of meanings, right? This disease and that disease and that disease, right? And then we can show that because this is provably true, and we can maybe set the prediction the coverage level to like 99%. Then the doctor can just go ahead and then definitely one of the diagnoses is right. So I think this gives lots of confidence to the decision-making process, right? But also, I also want to say that actually, when after this paper, I was thinking more about it in the drug discovery settings. Because in drug discovery setting, there's less of these problem of like prediction set or prediction interval. It's more of the settings of like selection. Like giving a large pool, want to select it to a small pool, and then we do some experiments, and then maybe you have some nice.
And there's a cost for the experiment, so you really need to select the right things.
Exactly. So we don't really care about each point's prediction set or interval, but we care about these large outcomes, like this maybe the small selection set from the machine learning model. It has some force discovery control, and then this force discovery control is very nice because now and I mean if we have some guarantees on this force discovery control, then it's very nice because now you can budget well. You can know ahead of time what are the errors fractions in it, and you can also adjust the threshold to do the experiments. So I think that would be very nice, and we're actually also working on that. So we have, I think, so our collaboration with Emmanuel, there's one of his students called Ying. She did a lot of work on conformal selected inference, and then we're now extending that to much more drug discovery problems. And I think we're able to see lots of interesting. We're able to like observe it has some empirical guarantees on the force discovery.